Okay, so I promised the team I'll do a recording of what I've been playing around with, and that was over the summer break, just looking at different ways of articulating facades using Grasshopper, and naturally not trying to do conventional facades, but something with a bit of gradients or difference, variation to it. And it's going to take you through a few images of the different facades I was playing with, the articulation, and then I'm just going to spend a little bit of time on how I generated the last one I'm going to show you now, which I'm quite proud of, because as an intermediate user I had to come up with a way of getting all my glazing panels to be planar, but we'll get back to that in a second. For now I'm just going to show you a few of the images. So this is the first version I did, which essentially just uses the graph mapper to get shading from, or shading devices, solar shading from a thicker element near the center of each side, getting thinner and thinner and more elegant towards a corner, so the corners open up and you're more aware of the glazing. And even the horizontal members that sweep around go from much wider to much thinner. So very simple, very elegant, but successful in my opinion. So moving on to the next one. The next one was a bit more forced in a way. Just something that's been done quite a bit before. Just trying to see whether it's achievable with Grasshopper. And I think the one feature that I do want to point out here is just the fact that the glazing is triangulated, which means that each panel is planar. So you could send this to a CNC machine or fabricator, and using Grasshopper you can, or any other computational design program, you can actually give locations for each one of these, whether it's on the first floor, second floor, all the way up to the top. And starting from one corner, you can actually see the seam generated in another vertical mullion over there, which I still have to design out of the script. But yeah, the whole idea was to get planar glazing panels, and then the actual cladding panels could be slightly bent, which is possible with your Korean facades and a few other products. Even some of the metals you could probably bend up to a certain degree. So yeah, that's just one view of it. Let's go to another view just slightly further back. That gives you that sinuous, almost pulsating facade effect. Not supposed to be a fully resolved design. You'll see there are no flaws, there's no proper internal circulation. It was purely just playing with facades. So yep, and then let's move to the next iteration. The next one was a bit more conventional, but what I tried to achieve here was have deep set windows, and if you look towards the sides, which would be the west elevation, similarly on the east elevation, I tried to get sort of serrated edges. So the glazing is facing, because we're southern hemisphere, facing north, and the solid panels facing south, so that in the summer months when the sun comes over and it goes low and very far past the east-west axis, you don't have that hot late afternoon sun baking into your potentially office space. So this facade was also a basic attempt at a little bit of a climate control and solar radiation control. Also quite wide horizontal bands, which creates that solar shading for your summer months when the sun is much higher. Just looking at another view of this one, but slightly closer up, just a flat on view. You can see it's also much more massive or heavy appearing facade, which could be granite slabs or stone type of element that's used. And also that grading effect from much more solid to more slender on the sides, until it gets to the serrated effect on the edges, where there's almost no view to the south, but you get views to the north, also just to modulate that daylight coming in. Then the final iteration I played with was just going going a bit more way out or radical in a sense. So I was looking at something that's more wavy, using a sine wave to modulate the facade, break it up into panels. That's just a basic render of that. And then I've got one more view which just shows that it's quite a dynamic facade. And once again, I just have to apologize. I mean, there's no roof articulation or anything. It's really just to show what's possible with the facades. So yes, having given you that extensive introduction, I'm just going to show how this particular version was modeled in Grasshopper, and how I managed to keep all of these glazing panels planar, which really helps with fabrication. So let's get on to that. Okay, great. So we're just going to look at how this was modeled in Grasshopper. I'll just take you through the process, and I'll have to remember a bit. It was 2 or 3 months ago. So let's just pick up from that. I think I'll go to just conventional mode, not rendered mode, so we only see one element at a time. And you can see that it's definitely a learning curve for me. I essentially start with a script and then I refine it until I find something that I believe works. And right up front, the idea would be to start with a form, because naturally with a visual script like this in Grasshopper, you could actually apply it to any form. So it could be an oval form, oval shape, which it happens to be now. Let's just go right towards the back and see what it looks like. So it's more an oval form, and that's how it is applied. But initially when I started, I actually worked with a more irregular form. So let's actually do that quickly. Let's just pull it across and see what it does if we move both of these elements to the other side. So now we don't have an oval form, we've got an irregular shape. And let's just give it a couple of seconds to calculate. And what you'll find is, if I select all of these just to make them visible, is that it's exactly the same design but applied to a different base form. So that's the one benefit of having a design script like this, regardless of the software you're using. If you're using computational design, it could be applied to any base form. So you could also have multiple buildings using the same script but looking very different. So yep, back to the scripts. So we started with this form, and first up I just deconstructed it, which of course is a very handy tool in computational design because it gives you the edges, the faces, etc., which you can further manipulate and work with. So in this instance, it gave us a base curve, it gave us a seam curve, and it gave us a top curve. But for this script, I basically developed most of it just on the base curve, which I'll come back to in a second. And then I also used the vertical seam curve just to create a height, an overall height of that shape. And then by using domain and range, and I'm not going to go into detail, you're probably familiar with some of these concepts. If not, we can discuss it some other time. But by using a domain and a range, we can use the height, which we determined over here. So let's just have a look at what it is. It's almost about 15 meters, which we telling the computer or the script to divide into three portions. And if you look at the result of that, it means that the bottom, we're starting at 0, then 4.93 meters is the next line, 9.8 is the next one, 14.8 is the final line. So we're creating essentially floors going vertically up. And what we did over here with the base curve was to take the base curve and then just to divide it up into equal segments. And I specifically went for equal segments so that the seam would coincide with one of the points. Otherwise, you sometimes end up with half a window, something like that. And I just added this little panel, it's called, showing how big each panel is. So it's just over 900 millimeters, which is quite a standard module for aluminium. So you can see the base curve now is subdivided into 260 panels. And then because we've already worked with the seam and divided the height, we can use these height offsets, which we already generated, and we can offset this base curve going upwards. Now, the first thing we need to do here is, if you look at it closely, I'm just going to click on this, is we've got a bunch of vertical lines. So we've got 260 points times 4. So it's 260 branches in terms of the data tree, which once again is obviously a whole series in itself. So I'm not going to pause on that to explain that. But essentially we've got 260 points right round, and they repeat vertically 4 times. So if you connect them, you get vertical lines. But what we want to do is to work with horizontal lines. So we're going to use the flip matrix component. And as you can see, if we do that, suddenly we end up with horizontal lines. Okay, so once we've got the horizontal lines, we've got 4 of them. Basically, it's a bit back to front, but 0 is a base and 3 is a top one. So 0 and 3 we're not going to manipulate much. We're just going to use these points later on. That's the base tier, that's top tier, but we are going to manipulate the intermediate ones. So the ones in the middle, those 2 we're going to manipulate, and we're doing that by using the graph mapper again. There are different ways of doing it. We could have used attractor points. Sometimes is probably better in terms of control, but for this option I use a graph mapper and use 2 different sine waves, one with a bit higher frequency and one with a lower frequency, and based on that I took these horizontal points and first of all I moved them vertically. So you can see there's a bit of a swerve and a curve that comes into that, and the same with the one slightly above it. So this is the second from bottom, this is second from top. So we've got the 2 straight lines. If I'm just going to click on them again, with the straight points, we've got the straight points, and then we've created wavy lines in between. So once we've got these, we also want these to move horizontally. So these vertically wavy lines, we work on them a little bit more. We use some components just to make sure we get a normal. So we've got a horizontal direction, which is always normal to that exact point where it's happening. So it doesn't move in random directions. And then based on that, we could give it an offset. So the original curve, you'll see is something like that. Let's just click on it individually. And then the offset curve has got a wavy pattern, which also moves in and out. Same with the other one. This is the original one, and that's a wavy one. So these are essentially the 2 curves that we're manipulating, or the sets of points, I could say. And then from that, we can start connecting them. So the base tier with the wavy tier, we can connect with lines. So that's the bottom segment of our building, of our facade. Then we've got a middle tier which sits on top of that, and then similarly we're using the wavy points we generated, and the topmost row, which is still coming from right in the beginning, where we've got a very simple straight row of points, which is a divided up curve. And if you connect all of them, you get the top segments. So we've got these 3 sets of lines which generate the different segments of the facade. From that, we just move on to creating the vertical fins from these guys. So basically all these lines you just saw, I combine them, and if you hover over it, it will tell you we've got 260 vertical lines, and it sees each one as an individual line. And then I just took those lines and extruded it in one direction and another direction. There's probably a more clever way of doing it in one go, but I just wanted to keep a glazing line sort of on that line that you see in the middle. I have a slight extrusion towards the inside of the building and a big extrusion to the outside. And then just using the union, what exactly is it called? Region union. command. I combined these two extrusions into one shape, and I just gave it a surface. So that's basically the essence of our facade. We've got these ribs, undulating ribs, pulsating ribs running right around the building. And from that we give it thickness. This is a pufferfish component, which is quite useful because a native one only offsets to one side. This one offsets to both sides to give it a thickness, and then we just gave it a color at the end as well, which you'll see. So that takes care of all our vertical ribs. And then the top component, I could have used our base geometry right up front, but I just took the ribs we created, use a discontinue component just to get the points over there, flip the matrix again so we're working horizontally, and then created this whole continuous curve for each floor. And then also maybe a lack of knowledge, maybe there's some other way of doing it, but because these lines aren't all planar, it's not a simple case of just offsetting them to the inside or the outside. So what I did rather is I extruded it vertically and extruded it horizontally to give it some thickness, and then once again using the pufferfish offset to give it thickness in the horizontal direction. So there we have a segmented horizontal beam. As you can see, an offset way of doing this might be slightly better because these extrusions actually end up having slight gaps in them, which I haven't fully resolved yet. That will be for the next iteration of the script. So okay, so that takes care of the ribs and the horizontals. So we've got quite a bit of the facade completed, and without too much scripting, actually not a lot of information going into that, or not a lot of components going into that. Then coming back to these lines we generated before, we just deconstructed them into their start points and end points, and by using all the start points and shifting the start points, you could generate a whole lot of horizontal lines, and doing exactly the same for the end points, using all the endpoints and using the same endpoints and just shifting my list. I can generally create a whole lot of horizontal lines as well from a series of points. And then I just used this edge, I think it's called edge surface, ruled surface, sorry, apologies. A ruled surface, so it's lines on the top, lines at the bottom, ruled surface. And now we've got these planes, which aren't fully planar, but fortunately Grasshopper recognized the outlines. I just used the curve component and it recognized the outlines. But then what I did is, because 3 points are always planar, like a table with 3 legs never wobbles because they always touch ground, I took basically the base lines which we generated, and then I took the end point on top, one of the end points, and I generated these planar triangles. And then the next step was really just to project these rectangles, which are closed rectangles, planes essentially, onto these triangular planar ones. So what you get then is a proper planar box. And if I compare it to the original, you'll see that there's, especially where there's much bigger, why am I not seeing it now? Let's compare these two. Yeah, okay, there's serrated edges near the top because it's perfectly planar, whereas the previous ones were just flat. These ones, each one of these boxes actually refers to a proper plane, which means all 4 corners are exactly on the same plane. And then I just did a test here, planarity or planar test, and we've got, if I just hover over here, we've got 260 values, 260 polyline curves, and it tells me here that all 260 of them are planar, so it was successful. And because these curves are planar, it's easy just to offset. So we've got the original one, we've got the offset, and then from these offset ones we can generate the frames on the edges, and we can also generate the glass planes. And then from there it's quite a simple exercise. The frames we also give thickness with the pufferfish component, And you can, you can see all the different planar frames there, which the script generated, and then the same for the glazing, which comes in between. And that essentially gives us a whole thing. Then I just did a color preview for the glass with a bit of color, gave it some transparency. And then if you select all 4 of these, that's the full facade over here. And let's just go to a rendered view. So there you go. We've got this waving and wavy pulsating facade with these ribs, horizontal members, and then inside we've got all these planar frames and glazing. As you can see, it probably needs a bit of further development. Occasionally you're going to find a bit of a gap, so maybe these horizontal members need to be slightly wider just to cover those gaps. And that's it. Let's just look at a few named views just to see what it looks like in 3 dimensions. So that's one view. That's quite a dynamic view over here, showing how these segments move up and down and in and out. Creates quite an interesting facade. And then, yeah, maybe just more of a close-up. So very dynamic, very easy to manufacture actually, and yeah, very much doable with Grasshopper. And that's it for this time. Thanks so much for listening.